let's talk some more about exponential functions and logs. That's what we were talking about last time. The natural log, ln of x, and e to the x are inverses. Right? One of them does the opposite of the other one. Now, in a typical presentation of the topic, if you learned about these things in high school, probably you learned about e to the x first, just because it's a little easier to explain. E to the x, e is a number, and you just do exponents of that number. Ln of x is a little harder to explain. What does the natural log even mean? The typical way to explain what the natural log means is just that it is the inverse of e to the x. So when I say the natural log of some number equals something, what that means is that the exponent of the other thing equals the first thing. It's the inverse of e to the x. We're going to do some particular examples with that today. But one thing in particular that this means is, and I think I wrote this explicitly last time, it means if you plug these functions into each other, they kind of cancel out. So one way is you could plug the exponential inside the log, or you could plug the log inside the exponent. Either way, you get x as the answer. This is what it means to say they're inverses, is that when you plug one inside of the other, they will cancel out and just give you what you started with. All right?
Is the natural log of the base
Yeah, so there are other logs with different bases. We say the natural log has base e because it corresponds to the exponential with base e. The other logs, like the base 10 log, is related to the 10 to the power x. We're going to talk about these later on today, if we get that far. All right, these are formulas about logs and e's, and we can sort of convert is what I meant to say. We can convert formulas. What I mean is, if you start with a formula that's written in terms of logs, here's a formula that's written in terms of a log. Can I rewrite that or convert that into a formula, the same formula but written in terms of exponents? This is just like when you write an ordinary function and its inverse. If I said f of x equals y, this is the same as saying f inverse of y equals x, right? And since log, like the ln, is the inverse of the e, you can do the same thing for this. Whenever you have a formula which has ln in it, this can be written equivalently. You rearrange everything. So the log is the inverse of the e. Sort of use this as your model. Can we rewrite this instead of using a log but using an e? The answer would be, in this example, e to the power 5 equals 2x plus 1. Right? You write the things in the other way around. You put the function on the other side, and you use the inverse. So any formula that's written in terms of a logarithm, you can write the same thing written in terms of an exponential function. This is what the kids these days, I don't know if you know this, but kids, like elementary school math curriculum is totally different now than when I was a kid, and I think it's different from when you were a kid. Sometimes I ask my kids what they're learning in school, and they say things that I've never heard of. But one time I asked my kid, "What are you doing in your math class?" And she said, "We learned about fact families." Fact families. Are you into that? I didn't know. I said, "What is?" No, fact families. There's a fact families. I said, "What does that mean?" And they were like, "You don't know what that means?" I said, "No, I don't know what that means." A fact family is, she was like, well, it's like if you say 2 plus 4 equals 6. That's the same as saying 6 minus 2 equals 4. Those are fact families because they mean the same thing. It's just written in a different way. That's a fact family. Isn't that cute? Anyway, all this to say, this is a fact family. Those two things, they mean the same thing. It's just you writing it in some rearranged version of the same fact that both are expressing because the log is the inverse of the e. All right? Well, we can convert the other way around also. How about if I start with the exponential function like this, e to the 3x squared equals 10? Anyone try to tell me what is the logarithm version of that formula? Yeah. Yeah, it's this way. ln of 10 equals 3x squared. There's sort of only a few choices of what it could be. But basically, you put the function on the other side from where it used to be, and you use the inverse instead of what it used to be. Yeah, ln of 10 equals 3x squared. Another way to think about this procedure is you could think of this as I'm doing the ln on both sides. You could say I'm going to do ln on the left side, ln e to the 3x squared. I don't know if you prefer thinking of it in this way. You can think it through this way too. And then you just simplify on the left. ln and the e cancel out, and you get 3x squared equals ln 10, which is what I said before. So if you like to think of it just in terms of do the same thing on both sides, then you can think of it that way too. Yeah, you take the log on both sides, and then you do the derivative. Yeah. Here I'm not doing any derivatives. I'm just trying to rewrite the same formula again in two different ways. The reason why you want to do this, actually this is super useful for solving for x in weird situations. So we can use this to solve for x in strange situations. What I mean by that is, for instance, if I have x in the exponent, that would look something like e, if I had something like this, e to the power x minus 2 equals 7, and you need to solve for x. Let's say you can use your calculator if you want to. The problem, even if you have a calculator, you still have to deal with the fact that the x is stuck inside the exponent. How do you get it out of there? Well, you rewrite this as a logarithm. Right? If you write it this way, now the x is no longer stuck inside the exponent, and I can actually solve for x here. And if you have a calculator, you can push the ln button and figure out what ln of 7 is, and then that's it. So to solve for x here, I mean, without a calculator, this is the best I can do, but I can type that into my calculator if I want to, and that's the solution. Without a natural log, there's really no way to get the x by itself on one side of the equation, starting from the beginning there, when the x is in the exponent. All right? And we can also use this to solve for x when x is inside of a log. So if x is inside a logarithm, you do a similar trick. How about this? 12 equals natural log of 10x minus 1. I want to solve for x. Put x by itself on one side. How do you get x out of the logarithm? Well, you don't really, but you rewrite this as an exponential instead of a logarithm. How do I write this instead as with the e somewhere? Yeah. Close. Yeah, it's got to be this way. This is something, it's a little confusing, but you put the function on the other side from where it used to be, and you use the inverse function. Great. This reminds me of an old math joke. Stupid math joke. Every math joke I know is stupid, but you ready for this joke? It's very short. The joke is, you look at this. Hey, can you solve this for x? The answer is, yes, I can solve it with ease. Get it? This is the e there. Yeah. It's better if you do it this way, if it's like 4 equals ln x, and then you say, I do e's on both sides, and then those cancel on the right, and I get x. The punchline hits better on that one. I did it with ease. There were two e's there. Yeah. All right. Anyway, can we just finish this one here? Solve for x would be, now you can easily solve for the x, right? Put the 1 over there, e to the 12 plus 1 equals 10x, and then divide by 10. And again, your calculator has an e button on it, so you could, if you really wanted to, you could type that into your calculator and have the value for x. All right? And this is really the purpose One of the purposes why logarithms were invented in the first place is because people want to deal with exponential functions in the real world, in science, whatever. They're very important. A lot of things in the real world obey formulas involving exponential functions. And if you want to solve those things for x, when x is inside the exponent, you need to use the logarithm. There isn't really another way to do it. All right. Any questions about that stuff? Great. Okay, let's talk about some basic simple rules for exponents. Everybody kind of knows these already, like you learned these in your youth. They are things like this: e to the x plus y equals e to the x, e to the y, right? E to the x minus y equals e to the x divided by e to the y, and e to the x to the r equals e to the rx. These rules are inspired by the same rules that we talked about for logarithms, right? But the log rules are the other way around. The rule for the exponent, say here, is when you have addition inside the exponent, it converts into multiplication outside the exponent, right? The log is the other way around. The log says when there's multiplication inside the log, it turns into addition outside the log, right? But this is not a surprise, right? You should expect everything that was true about the log sort of should still be true, but the other way around for exponents, because exponents are the inverses of logs. And in fact, you can prove these if you want to by doing this thing about rewriting things in terms of logs. So check it out. Let's just prove, this is very simple, of the first one using rules for logs. If I want, here's a little proof lingo here. I'm going to say WTS means I want to show. I want to show that e to the x plus y equals e to the x times e to the y. That is the same writing in terms of logarithms. If you say, you could say do the log on both sides and then cancel the log with the e on the left. Anyway, this is the same as saying x plus y equals the natural log of e to the x, e to the y. If you take the log on both sides, the ln on both sides, on the left you can cancel it because it'll be just ln of e to something. On the right, you get this more complicated, weird looking thing on the right hand side. But is there anything we can do to the right hand side? Can you simplify that at all? Pop the e's out. Well, I don't want to do that inside the exponent because that's what I'm trying to prove in the first place. So x times y. I think, no, not quite. We have here a log of two things being multiplied. Is there, anyone remember the rule of, is there a log rule that you use in that case? I believe we did talk about this, ln of, say, AB. You can do something with that, right? Yeah, it's ln of A plus ln of B. This is something we talked about last time. There is also a rule about the log of A to some power. You move the power into the coefficient, but that I'm not doing that right now. So do this rule here, right there. What's it look like? It looks like ln e to the x plus ln e to the y, right? And what is ln of e to the x? It is x. Yeah, this is what I said, the very first thing I said today. You know, the log should cancel the e. Plus ln e to the y is y, yeah. All right, so if you read this, this is what I said I wanted to show, right? I said ln of e to the x times e to the y is equal to x plus y. This is, I will say, just to finish this off like a proof. So ln of e to the x, e to the y equals x plus y. As desired. This is something you see people say, desired. Just to let you know. This is what I said I wanted to show, and I've been done showed it. That's what that little concluding phrase means. All right. The other ones, so this was only one of those rules, that I wrote at the top there. The other ones you would prove in a similar way, and I don't think we need to go through them, but take a log on both sides, and then you use some property of logs, and it gives you the property that you want for exponents. Any questions about that? Great. Now I know these are rules about exponents that you learned, like even in middle school, you probably learned those, or maybe even before. Probably not before. But I just wanted to demonstrate how these rules could also be deduced by using properties of logarithms. All right, let's talk about everything we've said so far about logs and exponents has not really been on the level of calculus because we haven't talked yet about derivatives or whatever. So let's talk about that of exponents at least. Derivative of e to the x. E to the x, you may already know, has one of the best derivative formulas ever. The derivative of e to the x. I want to know, so what is something like dy dx when y equals e to the x, right? This is what if I have y equals e to the x, what's the derivative of that? Now, if you don't know the answer, it's not so hard to figure this out. Again, it will come from writing this instead in terms of logarithms and then taking the derivative because we got to know what the derivative of the natural log is. So we're going to write y equals e to the x. This is the same. Writing as logarithms, it means x equals natural log of y. Writing the other way around. And then here we can take the derivative. Now do the derivative on both sides, and hopefully we can figure out what dy dx is. On the left side, we just get 1. The derivative of x is 1. And on the right side, derivative of ln y is going to be 1 over y times dy dx. I'm doing what they call the implicit derivative, which hopefully you learned about in Calc 1, although it's not really a big deal in this class. I'm only going to do it a few times, so if you haven't seen that trick before, that's all it is. And now we want to solve for dy dx. So multiply the y across. It says dy dx equals y, right? And of course, y, we started off by saying y equals e to the x. And this is our conclusion. So in conclusion, what is the derivative of e to the x? The derivative of e to the x is e to the x again, right? We started with e to the x. When you take the derivative, because of some kind of magic, you end up getting e to the x again as the answer of the derivative. All right? This is the great fact about e to the x. And from the point of view of a calculus class, this is kind of the big deal about e to the x. If your friends ask you, what's so great about the number e? You can tell them, like, e is just as good as, like, the number pi. Everybody kind of knows pi comes from geometry. I don't know if everybody knows that, but it does. What's so great about e? This is something you can say, although if your friends don't know what the derivative is, this won't mean anything. But derivative of e to the x equals e to the x. Actually, e to the x is the only function which is equal to its own derivative, apart from. So it's also true that any constant times e to the x, the derivative of any constant times e to the x is, again, the same constant times e to the x. But that's it. There are no other functions which are equal to their own derivative. Oh, I almost pushed the button with my leg. Just stay away from the button. Yeah. All right. The derivative of e to the x is e to the x. It's a great fact. Any questions about that? Great. You want to hear another math joke? This is also every math joke I know is stupid. This is a more elaborate math joke. It's about the land of the functions. They all live together in the forest, happily together. The functions, but there's a bridge in the land of the functions going across a river or something, and the functions all know you should not cross the bridge because it'll mess you up. Because when you cross the bridge, it takes the derivative. So like x squared crosses the bridge, turns into 2x. It messes you up. If a constant function crosses the bridge, it like kills them entirely because they become 0. So they all say like don't go across the bridge. And the one day a young function says, you know what, I'm going to go across the bridge because I have a good feeling about this. It's not going to mess me up. And they're like, no, it's going to mess you up. And the young function says, no, I'm e to the x. I can go across the bridge and nothing will happen. And e to the x goes across. This is not the joke. It's not over yet, if you can believe it. E to the x goes across the bridge and gets totally killed, turned into a 0. And everyone's like, oh no, what happened? And someone says, oh, you see, the bridge, it takes the derivative with respect to y. And so x was treated as a constant. So it became 0. Yeah. That's the joke. Hilarious, isn't it? Yeah. Yep. I suppose I didn't have to spend a minute telling that joke. I feel like I have some kind of, I don't know if you ever think about, I have some kind of moral problem with math jokes. Yeah, maybe. I feel like math jokes, at some level, are like an expression of my own superiority. Like, part of what makes it funny is that you know that you get it, and most other people wouldn't get it, but I get it, and that's why I'm so delighted to hear this math joke, because I'm so sophisticated and I know so much more than all those other idiots who wouldn't get it. I can, yeah, yeah. All right, that's my moral conundrum about math jokes. I think really it's not a big deal, but I have some kind of feeling about it. Okay, so the derivative of e to the x is e to the x. Now, typically, you don't just have e to the x. You usually have like some other stuff inside the exponent. So what do you get when you take the derivative of e with some other stuff inside the exponent? Well, you have to do the chain rule in that case. And the chain rule says you get the derivative of the outer thing, which is the e part. You get the same thing again. But then I got to multiply times the derivative of the inside, which is like that, right? And so, for example, the way this typically looks is something like if I want the derivative of e to the 3x squared plus 7x, you get the same thing again, first of all, and then times the derivative of the inside. And in this case, it would be 6x plus 7, like that. So this is a more typical example of using the derivative of e to the x. You get the same thing again, followed by times the derivative of whatever was on the inside. All right? I had some real quick ones. How about you guys try these? Individually, they are fairly straightforward. So find the derivative of each one with respect to x. Don't just say they're all 0 when you're doing with respect to y. How about e to the root x? How about e to the 3x over x squared plus 1? X e to the 5x, and e to the sine x. See what you think. I should have put that last one first. I think that last one is the easiest one.
Is it, the second one, is it actually minus 1 or plus 1?
It says plus there. Did I say minus?
No, I just.
Oh. Yeah, I think it's plus. Whatever you want. See if you can find the derivative. I'll give you a few moments. Maybe I'll walk around, see how you're doing. Don't mind me. You don't have to talk to me if you don't want to. Take another minute and then I'll talk about them. Folks at home doing all right? Yes, all right. All right, let's chat about these. So the last one I should have wrote first as I think the most straightforward one. Derivative of e to the sine x equals e to the sine x times cosine x. All right. By the way, would you mind a little picky comment? I saw several of you as I was walking around wrote this. E to the sine x equals e to the sine x times cosine x. That's not true. It's the derivative of e. It's this, right? If you don't write the derivative operation, then what you're writing is false. I mean, I know what you mean in the context, but oftentimes, like right before a test, a calculus student will ask me, just so I remember right, e to the x is e to the x, right? And I say, yes, but what you mean is the derivative of e to the x is e to the x. Oh, yeah, that's what I mean. It is also true that e to the x is e to the x, but that's not what you think it means. Okay, let's try e to the root x. Someone want to shout it out? What did you get for that?
E to the root x times x to the negative half.
Yes, e to the root x times 1/2 x to the negative 1/2. Great. That's the, this root x you realize is x to the 1/2, and then you take the derivative, you get 1/2 x to the minus half. Great. How about derivative of e to the 3x over x squared plus 1? This one you have to do the quotient rule, so you get e to the 3x over x squared plus 1. You always get the same function again, and then times the derivative of the inside times, anybody remember the quotient rule? Yes, I prefer ho d high minus high d ho over ho ho. That's how I learned it. Yeah, where high is the top and ho is the bottom. The bottom is, yeah, so if you do all that, it's the bottom times the derivative of the top, which is 3, minus the top times the derivative of the bottom, which is 6x, over the bottom squared. Like that, right? I hope you got that. This is the quotient rule. And then how did you handle x times e to the 5x? Yes, you did the product rule, right? Yeah, you got to do the product rule here. So you go, the first thing, there's different ways to write the product rule, but I would say it's the first thing times derivative of the second part. So the derivative of e to the 5x is e to the 5x times 5. And then plus the second part, which is e to the 5x, times derivative of the first part, which is 1. So this, I think this is what he said, 5x e to the 5x plus e to the 5x. Yep, hope you got something like that. Great. These are all fairly simple. I mean, just reviewing our basic derivative tricks. Any questions about any of that? Okay, the derivative of e to the x is e to the x, right? And so what that means is also the antiderivative of e to the x is e to the x, right? If you take the derivative of e to the x, you get the same thing again. That means if you were to take the antiderivative, which is the opposite of the derivative, you get the same thing again. Of course, you always get the plus c when you take the antiderivative. This also is a useful formula. And, as written, it's not very interesting. It's more interesting when you have other stuff inside the exponent. And in that case, you typically would want to do a u substitution. So I thought maybe we'd do one example like that. So an example which uses that formula. How about the integral of x squared e to the 3x, e to the x cubed minus 1. How about that? So I got serious lag with my screen here. X squared e to the x cubed minus 1 dx. Since we have extra stuff inside the exponent, we're going to have to do a substitution. And I would suggest the substitution, make the u equal to the whole exponent, right? Because I only know how to do integral of e to the x. So I'm going to make the u equal x cubed minus 1, which means the du is 3x squared dx. If I divide the 3, it says 1/3 du equals x squared dx. And I have a good feeling about that because I see an x squared hanging out inside the integral here. And so I think the u substitution is going to work out just fine. If I plug in the u just directly where it goes, it looks like this, x squared and then e to the u. I don't know why my screen is lagging. If I rearrange it, I can put e to the u first, and then what remains is x squared dx. Oh, it's unbelievable how slow my screen is. And then, yeah, plugging in x squared dx, sorry, I'm getting distracted, is 1/3 du. So it's going to be e to the u times 1/3 du. Right? Then I can factor the 1/3 out, like we always do. Integral e to the u du. And that's the end of the substitution. Now we can finally actually do the antiderivative. What do you get after doing the antiderivative? I'm not sure. It sounds like you're saying something like the derivative. Derivative, but yeah, we're doing the antiderivative here. Perhaps using this formula in the box up there. Yeah, it's going to be 1/3 again, but then e to the u plus c. Integral of e to the u is e to the u, right? It looks like I didn't really do anything in that step, or I just like erased the integral sign. In fact, we did do the integral. It so happens that you end up with the same thing again. And then just last step, as always, we'll plug the x value back in. So 1/3 e to the x cubed minus 1 plus c. And that'll do it. All right. Any thoughts about that? All right. We got about 15 minutes left. We can start talking about the next little bit here. The next section is about logs and exponents or exponential functions with other bases. Logs and exponential functions with other bases. This is what someone was asking about earlier. You all probably know there are other logarithms, not just the natural log, but there are other ones. They are the logarithms with other bases. And there are other exponential functions with other bases. And these actually are a little easier to talk about. So let's talk about exponentials first of all. We say e to the x is the exponential function with base, the terminology, base e. Base means like this downstairs number in the exponent. This is the base. And of course, the upstairs is the exponent, right? The one down there is called the base. The one up there is called the exponent. So this e to the x is the exponential function with base e. But of course, we can do similar things using other bases. So other bases would look like, you know, this function, 2 to the x, or 10 to the x, or, you know, you can put whatever number you like in the base. Those give you other exponential functions with other bases, all right? I don't know if you ever thought about these functions. They don't look so weird, 2 to the power x. It just means whatever the x value is, you plug that in the exponent. It's a little strange to wonder about this as a function where you can plug any net value for x in. So here's what I mean by this. 2 to the power 3, what does that mean? It means 2 times 2 times 2, which is 8, of course, right? And you could plug any positive number into that exponent. You could also plug a negative number, 2 to the power negative 4. This means 1 over 2 to the 4, which means 1 over 2 times 2 times 2 times 2, which is 1 over 16, all right? But if I write this as a function, 2 to the power x, where you can plug any number in the exponent, you should ask yourself, what exactly does that mean when I plug any number into the exponent? Like, for instance, could I plug 1/3 into the exponent? What does that mean? 2 times itself 1/3 times. Yeah, this actually is the cube root. So you no longer think of this as 2 times 2 times 2 over and over again, but it has a different meaning, I guess. This means the cube root of 2. What about some other function, some other fraction? How about 2 to the 5/6? What does that mean? Does that mean anything? Yeah, so this is another thing you learn in high school or whatever. This is the same as that. Or it's actually equal, if you don't like it that way. It's equal to this. Oh, no. Yeah, that's right. Yeah. So you can really plug any number you want in there, right? Actually, how about this? Have you ever thought about this before? I don't know. This means 2. I mean, it doesn't really mean 2 times 2 times 2 over and over again, pi times. But it also, because pi is an irrational number, pi cannot be written as any fraction. And so this cannot be written as anything like that. A radical sign together with an exponent. What does that even mean? Anybody ever thought about this before? That is a thing. Like there is such a thing as 2 to the pi, but well, I'm about to say what that means. So you could do something like, so if you wanted to do 2 to the 3.14, I would write this as, instead as 2 to the 3, I think this might be similar to what you were suggesting, although as written it doesn't look anything like what you said. But if you think about it 3.14, then you can say this is just, another way you could write this is 2 to the 3 times 2 to the 0.14, and then make this like 8 times some weird leftover part.
That's what I was saying.
Yeah, this is more like what you were saying. But you might as well just go all the way to this being sort of the leftover part. This would work for 2 to the power 3.14, but of course pi is not equal to that. It's close to that, but not quite equal to that. One way you could do this as some kind of limit, you could define 2 to the pi as equal to the limit of, say, these numbers, 2 to the 3, and then 2 to the 3.1, 2 to the 3.14, 2 to the 3.141, etc. You keep on doing those rational exponents, and eventually maybe it approaches a particular value, although does that even have a limit? Like maybe this, it probably doesn't go to infinity, but there's no guarantee that those numbers actually approach a specific value. This is one way you could think about it. Actually, there's another way to think about this, which is going to work out great for our purposes. We will define, I'll just tell you how we're going to do this. 2 to the power x, no matter what x is, you're going to always do it this way. E to the power x ln 2. This you could think of as like a rule for exponents, but we're going to treat this like a definition. 2 to the power x is equal to e to the x ln 2. And so in particular, 2 to the power pi, its definition is this, e to the pi ln 2. Now, you might ask me just the same question. Well, if 2 to the pi doesn't really mean anything, isn't this also kind of meaningless? This may be even worse. You have e, which is a number, but then this inside the exponent. What does that even mean? Well, what this means is this is the inverse of the natural log, right? So what this means, so e to the pi ln 2 means some y value with ln of y equals pi ln 2. And this has a specific meaning because it would be the area under the curve. Remember, that's what our definition of ln y is. It's the area under the curve of 1 over x. And so what this means is, very specifically, it's some value here which makes this blue area equal to that number. And that's the definition. This is not a usable definition at all, but it is it is some meaning to this number, 2 to the power pi. That's what it means. This is very strange, but very strange, and in practice you don't think about it like this at all. If you really, in your real life, if you want to know what 2 to the pi is, you just plug it into the calculator and you get 10 digits worth of it, and that's good enough for anything you might want to actually do in the real world. But if you care about definitions, which I do from time to time, this technically is what the definition means. Any thoughts about that? Strange to think about. Anyway, here's the definition. So a exponential function with another base let's say generally with base b, this is a definition, is b to the x, and its definition is e to the x ln b, all right? And this works for any b which is greater than 0. The reason the b has to be greater than 0 is because in here, as part of the definition, I'm doing ln of b. And so remember, the natural log is only defined for positive numbers. You can't plug a negative number into the ln. And so this definition is only going to work when the b is positive. All right? Works for any b greater than 0. Yeah, I don't know if you thought about that either. It doesn't really make sense to talk about this when the base is negative. For example, if you allow the base to be negative, you would get something like this, which means the square root of -1, which isn't a real number. So that's why the base, if you allow negative bases, you get some very weird things can happen. So for our purposes, don't go there. You probably know there is such a thing as people who like to talk about the square root of -1. It's called the imaginary numbers, and you know, that's a real thing, but we're not going to get into that in this class, okay? I think we got a few more minutes, enough time to talk about some rules for these exponential functions. They obey the same rules as the natural exponential, that is the one with the e down there. The other ones with other bases, they obey the same rules. So I'm just going to write these down. B to the x plus y equals b to the x times b to the y. Also, b to the x minus y is b to the x divided by b to the y. Also, b to the x to the power r is b to the xr. And one other that we didn't write before is this. AB to the x. Anybody remember what's the appropriate rule for this? Yeah, a to the x times b to the x. Right. So these are a bunch of rules for exponential functions using a different base. And these are actually very easy to demonstrate using our definition in the box up there. So I'm going to look, can we demonstrate the first one there? I'm going to say the proof of the first one. And I think I'm going to give you another one of these to do on the homework. I think you'll agree with me. This is easy to do. You start with b to the x plus y. Can I rewrite that by plugging into the box up top? What is it going to say if I rewrite by plugging into the formula in the box? Start with e. Yeah, e to the power x plus y ln b. Okay. Anything I can do with that? Sure. Let me say, this is not exactly what you said, but I think this is what you meant. You can distribute inside the exponent, right? E to the x ln b plus y ln b. And then, can we do anything with that? You got to remember, is there a rule about e, and then inside the exponent you have addition up there? What does that look like? Yeah, break it up. How exactly did we break it up? Yeah, times e to the x ln b times e to the y ln b. Great. And then each of those is using the formula in the box again, which you can't see anymore. This is b to the x times b to the y. And that's what I wanted, right? We started with b to the x plus y, and we ended up with b to the x times b to the y, which is what we wanted to see at the end there. Excellent. I think maybe, I'm going to say one more thing. Unless are there any questions about that? Exponential functions with different bases. Can we do the derivative of b to the power x? Now, when it's e to the x, you get e to the x again. When it's b to the x, hopefully you get something nice. It turns out you don't just get b to the x again. But the way to do this is we use the definition of b to the x. The definition is e to the x ln b, right? And then can we take the derivative of that? I think we can. I mean, we did all those examples a few moments ago. It's the derivative of e to some stuff. The thing inside the exponent is not just x, but we're going to do the chain rule, right? So we get e to the x ln b times the derivative of the inside of the exponent. What do you think? This is a little strange because we have the x up there and also the b. I'm taking the derivative where x is the variable, which means this ln b, you should think of it as a constant, right? Whatever the b is, you could plug that into your calculator if you get some number. So anyone want to say, what's the derivative of the inside of the exponent here? So the x becomes a 1, but then what happens to this thing? So when I see x times ln b, that's what I see up there, right? ln b is a constant. So this is as if it said something like x times 3, right? And what would the derivative of that be? It would be 3 because of the x there, right? This, of course, more often would be written like 3x. Sorry. Look at that lag. 3x, right? And you take the derivative, the x goes away, you just get whatever the constant was. So when I have x times ln b, you take the derivative of that, the x becomes like a 1, and the constant ln b is the answer. It's like this. But then this e to the x ln b, of course, that is b to the x. So my final answer, and I will leave you with this, derivative of b to the x is b to the x ln b. All right. There it is, the formula. B to the x ln b. All right. And I think that'll do. Thank you for your attention. I hope you have a good weekend. See you next time. So remember, every Tuesday is going to be remote. So don't come here on Tuesday. I suppose you could if you want, but you will tune in on Zoom. Yeah, you can still come to the classroom if your roommates are pestering you. All right, see you. Mm-hmm.
Thank you.
Bye-bye, folks. Bye-bye.
Thank you.
See you. Yeah, you too. Sure.
Any way you can post the notes that you're writing? Like your, like post them in a form that I can print them out. Because I know you have lots of videos, and I was watching those videos. If you're going to check out my quiz later, it's not good.
Okay.
I did not study enough for that because I didn't study enough. I really struggled with the washer section of shells. I'm pretty sure I did much better on.
Yeah.
Just because I conceptually understand the function a little bit more.
Right.
The washers are a little bit confusing because I feel like when you slice things up into those washers, they kind of get distorted in a way and it just like messes with the way that I think about it.
Yeah, those are tricky. It seemed like other people didn't do something about it either.
Yeah, like you're gonna see it. It was very bad. I used 0 as my outlet radius because I was completely unsure of what I was going for.
Okay.
And I guess I think I was x squared is my inner radius, or x is my inner radius. Even vice versa, but it wasn't a good attempt at that question.
All right, I'll look it over. Yeah, I think I'm using this app, which is like
So you
a
know, go over
big thing. So I'm not sure if I can. I might be able to export it like a design or something.
Yeah,
I'll look into it.
all right, awesome. Thank you so much. I really appreciate it.
Sure.
This class is cool. I never really the first off, I never thought I'd make it this far in math, but Calc 1 really got me interested in mathematics and things.
All right.
I'm trying to maybe go into a math major.
Yeah. Cool. All right. See you. Hello.